Welcome to today's problem discussion. We'll be diving into problem number 503, next greater element 2. In this problem, we'll explore an efficient way to determine the next greater element for each number in a circular array. Stay tuned as we break it down step by step. In this problem, we are tasked with finding the next greater element for each number in a circular integer array. A circular array means that the last element connects back to the first, so the traversal effectively wraps around when necessary. For each element in the array, we need to identify the first number greater than the current one as we move clockwise through the array. If no such number exists, we return -1 for that element. The input is an integer array nums with a length between 1 and 10 to the power of 4, and each element falls within the range of -10 to the power of 9 to 10 to the power of 9. The output should be an array of the same length, where each element represents the next greater number for the corresponding input element. If no greater number exists, the result for that index will be -1. To understand this better, let's consider a few examples. In the first example, we have the input nums equals 1, 2, 1. For the first number, 1, the next greater element is 2, which is the very next number in the array. For the second number, 2, there is no greater number as we traverse the circular array, so the result for this index is -1. Finally, for the third number, which is also 1, we wrap around the array and find that the next greater number is again 2. This gives us the final result, 2, -1, 2. Now, in another example with nums equals 5, 4, 3, 2, 1, the array is strictly decreasing. For the first number, 5, there is no greater number anywhere in the circular array, so we return -1. However, for all other numbers, the next greater element is 5, since it's the largest value and comes before them in the circular traversal. This results in -1, 5, 5, 5, 5. Expanding on these examples, for nums equals 5, 4, 3, 2, 1, the reasoning is as follows. For the first element, 5, no greater element exists, so the result is -1. For the second element, 4, the next greater element is 5. Similarly, for 3, 2, and 1, the next greater element for each is also 5. This happens because we wrap around the array, and 5 is the first number greater than these values. Now, consider a different example where all elements are equal, such as nums equals 2, 2, 2. Here, no element has a greater number, so the result for each is -1. This gives us the output, -1, -1, -1. Since this is a circular array, it's important to remember that the traversal wraps back to the beginning when searching for the next greater element. Some edge cases to keep in mind include single-element arrays, where the result will always be -1, because there are no other elements. For arrays where all elements are identical, like 2, 2, 2, the result will also be all -1, as no element has a greater counterpart. In strictly descending arrays, such as 5, 4, 3, 2, 1, only the first element will have a result of -1, while all others will point to the first element as their next greater value. Another key scenario involves wrapping around the array, as in 1, 3, 2. Here, the next greater element for 1 is 3, but for 3, no greater number exists, so the result is -1. Finally, for the last element 2, wrapping around discovers 3 as the next greater number. Handling these edge cases correctly is essential for solving the problem efficiently. To solve the problem of finding the next greater element in a circular array, one straightforward approach is the brute force method. The intuition here is simple. For each element in the array, we systematically check every other element to find the next greater one. Since the array is circular, this includes wrapping around to the beginning once we reach the end. The steps involve iterating over each element, scanning forward in the array, and looping back if necessary until we find a greater element or exhaust all possibilities. While this approach is easy to understand and implement, it has significant drawbacks. The time complexity is n squared, because, for each element, we could potentially examine all other elements. It is also worth noting that the space complexity is 1, as no additional data structures are used. However, the inefficiency of this approach, especially for large arrays, and its inability to fully take advantage of the circular nature of the problem make it less desirable. This is why we need a more optimized solution. A better solution is to use an optimized approach with a monotonic stack. This method leverages the stack to efficiently track unresolved elements while also handling the circular property of the array. The key insight is that by simulating 2 passes over the array, we can mimic the wrapping behavior without explicitly performing additional operations. For this, we use the index modulo the array length, ensuring we stay within bounds. The monotonic stack, which keeps indices of elements in a non-increasing order, allows us to quickly identify the next greater element. As we iterate through the array twice, we compare the current element with the element at the top of the stack. If the current element is greater, we update the result for that index and remove it from the stack. This process continues until no greater element is found or the stack is empty. At the end of this process, the stack contains indices for which no greater element exists, and these remain unchanged in the result array. This approach is highly efficient, with a time complexity of O(n), since each element is pushed and popped from the stack at most once, and a space complexity of O(n) for the stack and result array. The monotonic stack approach is particularly well suited for this problem due to its efficiency and simplicity in handling the circular nature of the array. By simulating 2 passes, we avoid the need for complex logic to wrap indices, making the implementation cleaner. Additionally, by minimizing redundant comparisons, the stack ensures that we only process each element a limited number of times. These factors combine to make the monotonic stack approach optimal for this problem. While the extra space requirement of O(n) may seem like a trade-off, it is a reasonable compromise given the significant reduction in time complexity from O(n)² to O(n). Though the implementation is slightly more complex than the brute force method, the performance improvements make it the clear choice for large input sizes, ensuring scalability and efficiency. Other alternatives, such as sorting-based or heap-based approaches, are not well suited to the circular property of the array. These methods would require additional steps to simulate wrapping behavior, leading to unnecessary complexity. The brute force approach, while simple, is far too slow for large inputs due to its quadratic time complexity. The monotonic stack approach stands out as the most efficient and scalable solution. It effectively balances time and space complexity while elegantly handling the challenges posed by the circular array. By leveraging the stack and simulating 2 passes, it avoids redundant computations and ensures optimal performance. Ultimately, this makes the monotonic stack approach the best choice for solving LeetCode problem number 503, next greater element 2. The task at hand is to determine the next greater element for every element in a circular array. This means that for each element in the array, we need to find the first element that appears after it, either in the same traversal or after wrapping around, and is greater in value. If no such element exists, the result for that position should be -1. To solve this, the brute force approach involves checking every possible pair of elements to find the next greater value. Here's how it works step by step. First, we iterate through each element in the array using an outer loop. For each element at index I, we launch an inner loop starting at the next index, I+1, to search for the next greater element. If the inner loop reaches the end of the array, we wrap around to the beginning using modular arithmetic to simulate the circular nature of the array. During this inner loop, we compare each element against the current element nums, I. If we find a greater element, we record it in the result array and stop the inner loop. If the inner loop completes without finding such an element, we assign -1 to the result at that position. To handle edge cases, if the array is empty, we simply return an empty result since there's nothing to process. Similarly, if all elements in the array are equal, there are no greater elements for any position, so the result for every element will be -1. However, this brute force approach has a major drawback. It involves 2 nested loops, meaning its time complexity is O(n)². This can become very inefficient as the size of the array grows. To improve upon this, we turn to an optimized approach that makes use of a monotonic stack. The core insight here is that the brute force method repeatedly traverses the circular array, leading to redundant comparisons. Instead, by leveraging a monotonic decreasing stack, we can efficiently track indices of elements for which we haven't yet found the next greater element. Additionally, we simulate the circular nature of the array by considering the array twice, effectively doubling it. This allows us to avoid explicit modular arithmetic and simplifies how we process the data. The optimized approach relies on the stack to manage indices of elements in decreasing order of their values. This ensures that at any given moment, the top of the stack represents the smallest unprocessed element. As we traverse the doubled array, for each element, we check it against the value at the index stored at the top of the stack. If the current element is greater, we've found the next greater element for the index at the top of the stack. We then pop the stack and record the result for that index. This process continues until either the stack is empty or no greater element is found. Once the comparisons are complete, we push the current index onto the stack, as it might be a candidate for future comparisons. Finally, since the array is doubled, we only store results for the original array indices, ensuring the output is the same length as the input. The efficiency of this approach comes from the fact that each element is pushed and popped from the stack at most once, leading to a time complexity of O(n). The space complexity is also O(n) due to the stack. This approach highlights several key insights. First, by doubling the array, we simplify the handling of its circular nature. We avoid the need for modular arithmetic while ensuring we process every possible pairing of elements. Second, the monotonic stack is central to the optimization. By maintaining a stack of indices in decreasing order of their values, we efficiently track candidates for the next greater element, reducing redundant comparisons. Lastly, the efficiency of this approach is evident in its reduced time complexity, which drops from O(n) squared to O(n). By processing each element in constant time, the algorithm is far more scalable for larger arrays. To support the implementation, we use two key data structures, a stack and a result array. The stack stores indices of elements that await their next greater element, while the result array is initialized with -1 and updated as we find greater elements. To visualize the algorithm, consider the input nums equals 1, 2, 1. We start with an empty stack and traverse the doubled array, which becomes 1, 2, 1, 1, 2, 1. As we iterate through this array, we push indices onto the stack and pop them when a greater element is found. For example, when we encounter the second element, 2, it's greater than the first element, 1, so we pop the stack and update the result for the first position. The process continues until all elements in the original array are processed. The final output for this example is 2, -1, 2, where each value represents the next greater element for the corresponding index in the input. This demonstrates how the algorithm efficiently handles the circular property of the array and avoids unnecessary computations. This Python solution uses a monotonic stack to efficiently solve the circular array problem of finding the next greater element for each element in the array. Here's a step-by-step explanation. 1. Initialization asterisk. Result is initialized as an array of -1s, representing the default value if no greater element is found. Stack is used to maintain indices of elements in a decreasing order based on their values. 2. Circular array iteration asterisk. We iterate through the array twice, 2*n. The modulo operation, I%n, ensures we simulate the circular nature of the array. 3. Finding the next greater element asterisk. While the stack is not empty and the current element, nums, current_index, is greater than the element at the index stored at the top of the stack, we pop the stack and update the result array for the popped index. This step ensures that we find the next greater element for all indices in a monotonically decreasing order. 4. Pushing indices asterisk. Indices are pushed to the stack during the first pass, I<n. This avoids unnecessary duplication during the second pass. 5. Final result asterisk. Once the iteration completes, the result array contains the next greater elements for all indices, with -1 for those that have no greater element. This approach has a time complexity of O(n), because each index is pushed and popped from the stack at most once, and a space complexity of O(n) for the stack and result array. Here, we begin with the Java implementation for the next greater element 2 problem. First, we import the necessary packages, specifically java.util, which provides the data structures we'll need. Inside the solution class, the method nextGreaterElements takes in an integer array, nums, as input, and we start by determining its length, stored in the variable n. We initialize the result array with the same size as nums, filling all its elements with -1. This is because, if no next greater element is found for a position, it should remain -1 as per the problem requirements. Next, we declare a stack using the dec interface, which will help us maintain indices in a monotonic decreasing order. This stack will be central to efficiently finding the next greater element. The for loop iterates over the array twice. This is done to simulate the circular behavior of the array. Within the loop, we use the modulo operator to calculate the current index, which wraps around when the loop exceeds the first n elements. This ensures we can treat the array as if it were circular. Now, within the loop, we use a while condition to process the stack. The goal here is to maintain decreasing order in the stack. If the current number is greater than the number at the index stored at the top of the stack, we pop the stack and update the result array at that index. This means we've found the next greater element for that position. After this, we check if we are in the first pass of the array, i.e., the first n iterations. Only during this phase do we push the current index onto the stack. This ensures the stack contains only indices of the original array and avoids redundant processing during the second pass. Once the loop finishes, the result array contains the next greater elements for all positions, or -1 for those where no greater element exists. Finally, we return the result array, completing the implementation. Let's start with the first example where the input array is 1, 2, 1. First, we initialize our variables. The length of the array, n, is 3. We create a result array initialized to -1, -1, -1, which will store the next greater elements for each index, and an empty stack to help us process the indices. Now, we begin the first pass through the array, iterating from I equals 0 to I equals 2. For I equals 0, the current index is 0, and the value at that index is 1. Since the stack is empty, we simply push the index 0 onto the stack. Moving to I equals 1, the current index is 1, and the value is 2. Here, we compare 2 with the value at the index stored at the top of the stack. Since 2 is greater than 1, we pop index 0 from the stack and update result 0 to 2. We then push the current index 1 onto the stack. Finally, for I equals 2, the current index is 2, and the value is 1. This time, the value at the top of the stack is 2, which is greater than 1, so we push index 2 onto the stack without making any changes to the result. At the end of this pass, the stack contains 1, 2, and the result array is updated to 2, -1, -1. Next, we proceed with the second pass through the array, iterating from I equals 3 to I equals 5. For I equals 3, the current index wraps around to 0, and the value is 1. Since the value at the top of the stack, which corresponds to index 2, is also 1, no changes are made. Moving to I equals 4, the current index is 1, and the value is 2. Here, we see that the value at the top of the stack, corresponding to index 2, is 1, which is less than 2. So, we pop index 2 from the stack and update result 2 to 2. Now, the stack contains only index 1. For I equals 5, the current index wraps around to 2, and the value is 1. This time, the value at the top of the stack is 2, which is greater than the current value, so no changes are made. At the end of this pass, the stack is 1, and the result array is finalized as 2, -1, 2. Now let's look at the second example, where the input array is 3, 8, 4, 1. We begin by initializing our variables. The length of the array, n, is 4. The result array is initialized to -1, -1, -1, -1, and the stack is empty. In the first pass, we iterate from I equals 0 to I equals 3. For I equals 0, we push the index 0 onto the stack since it is empty. The stack becomes 0. For I equals 1, the current value is 8, which is greater than the value at index 0 in the stack. We pop index 0 and update result 0 to 8. Then, we push index 1 onto the stack, making it 1. For I equals 2, the value is 4. Since 4 is less than the value at the top of the stack, index 1, we simply push index 2 onto the stack. The stack becomes 1, 2. Finally, for I equals 3, the value is 1. Again, since 1 is less than the value at the top of the stack, we push index 3 onto the stack, resulting in 1, 2, 3. At the end of the first pass, the result array remains -1, -1, -1, -1. In the second pass, we iterate from I equals 4 to I equals 6. For I equals 4, the current index is 0, and the value is 3. Since 3 is not greater than the value at the top of the stack, no changes are made. For I equals 5, the current index is 1, and the value is 8. Here, the value at the top of the stack, corresponding to index 3, is 1, which is less than 8. So, we pop index 3 from the stack and update result, 3, to 8. The stack then becomes 1, 2. Continuing, the value at the top of the stack is 4, which is also less than 8. We pop index 2 and update result, 2, to 8. The stack is now 1. Finally, for I equals 6, the current index is 2, and the value is 4. Since 4 is not less than the value at the top of the stack, no further changes are made. At the end of the second pass, the stack is 1, and the result array is finalized as 8, minus 1, 8, 8. When analyzing the time complexity of this algorithm, we start with the outer loop. The loop runs for 2*n iterations to simulate the circular nature of the array. Since accessing an index using modulo, like I%n, takes constant time, the total contribution from the loop is O(n). Next, consider the stack operations. Each element in the array is pushed onto the stack at most once and popped at most once. Since each of these operations is O(1), all stack operations combined also contribute O(n). Putting these together, the outer loop and the stack operations both contribute O(n), and their sum is still O(n). Therefore, the overall time complexity of the algorithm is O(n). Now, let's examine the space complexity. The algorithm uses two main data structures. First, the result array, which stores the next greater element for each index. Since it has the same size as the input array nums, it requires O(n) space. Second, there's the stack, which stores the indices of the elements in nums. In the worst case, such as when the array is strictly decreasing, all n indices may end up in the stack at once. This also contributes O(n) space. Apart from these, no additional space is used. Combining both, the overall space complexity of the algorithm is O(n). Let's break down the algorithm's behavior in different cases. In the best case, where the array is sorted in increasing order, each element is immediately popped from the stack after being pushed. While the stack never grows large, the algorithm still traverses the array twice, so the time complexity remains O(n), and the space complexity is O(n). In the worst case, where the array is sorted in strictly decreasing order, all elements are pushed onto the stack during the first iteration and popped during the second. Even so, the time and space complexities both remain O(n). For an average, random array, the behavior closely resembles the worst case, as each element is still pushed and popped once. Regardless of the case, the time and space complexities remain consistent at O(n). Finally, let's compare this approach to a brute force solution. In a brute force method, for each element, you would iterate through the array to find its next greater element. With n elements in each requiring a linear search, this results in a time complexity of O(n squared). In contrast, the monotonic stack approach reduces this to O(n) by ensuring that each element is processed only once, either being pushed or popped from the stack. This eliminates redundant computations, making the algorithm significantly more efficient for larger arrays. In terms of space, both methods require O(n) for the result array, but the stack-based approach adds a small, proportional overhead for the stack. This makes the stack-based solution both time-efficient and space-efficient, with an overall time complexity of O(n) and space complexity of O(n). When solving this problem, there are some common mistakes to watch out for. First, it's essential to account for the circular nature of the array. Many candidates overlook this and end up with incorrect results, especially for elements near the end of the array. To handle this properly, modular arithmetic, such as I+1%n, can ensure you wrap around to the beginning of the array as needed. Next, while a brute force O(n squared) approach might be a good starting point, it's inefficient for larger inputs and often leads to timeouts. Optimizing your solution with a stack-based approach is critical for scalability. Another common pitfall is mishandling duplicate values. If the array contains duplicates, your logic must ensure the correct next greater element is identified for all occurrences, rather than relying on assumptions about uniqueness. Finally, remember to initialize your result array properly. Assigning a default value like -1 ensures that elements without a next greater value are handled correctly and your output is complete. Overcomplicating the stack-based solution is another frequent mistake. The monotonic stack approach works best when the stack is maintained in a strictly decreasing order, ensuring efficient lookups. Adding unnecessary complexity to the stack logic can lead to confusion or inefficiency. Now, from an interview perspective, recognizing the pattern behind next greater element problems is key. Many of these problems can be simplified significantly by applying the monotonic stack technique, reducing the time complexity to O(n). It's also important to demonstrate awareness of edge cases during your explanation, such as handling empty arrays, single-element arrays, or arrays with all identical elements. Interviewers often look for your ability to articulate trade-offs. For example, while the brute force approach may demonstrate a basic understanding, they usually expect you to optimize and explain why the stack-based solution is superior in terms of time and space complexity. Lastly, clearly verbalizing your thought process, such as how the stack tracks potential candidates for the next greater element and how modular arithmetic helps handle the circular nature, can leave a strong impression on your interviewer. To deepen your understanding, it's helpful to explore related problems that use similar techniques. For example, LeetCode 503, Next Greater Element 2, is the problem we're discussing, and it directly involves the circular array variation with a monotonic stack approach. LeetCode 496, Next Greater Element I, is a simpler version where the input is not circular, but the same stack-based strategy applies. Another interesting problem is LeetCode 739, Daily Temperatures, which also utilizes the monotonic stack to find the next day with a higher temperature. Finally, LeetCode 901, Online Stock Span, is a variation of this concept applied to stock prices, where the challenge is to calculate efficient spans. These problems all share a common theme of leveraging a stack to efficiently solve next greater type questions, so practicing them can help solidify your grasp of this important pattern. When it comes to solving this problem, there are several approaches to consider, each with its own trade-offs. The brute force method is the simplest to implement, with a time complexity of O(n²) and constant space usage. However, it's highly inefficient for larger inputs and is best suited for small test cases or as an initial step to understand the problem. The monotonic stack approach, on the other hand, is far more efficient, with a time complexity of O(n) and a space complexity of O(n) for the stack. This method is scalable and ideal for larger inputs, but it requires careful handling of the circular array using modular arithmetic. An alternative is the optimized circular traversal with array doubling. Here, you conceptually simplify the circular property by creating a duplicated array, which avoids modular arithmetic but requires extra space. This approach also runs in O(n) time but comes with an additional memory cost. Understanding these trade-offs will help you choose the most appropriate solution based on the constraints and requirements of the problem. Great job making it to the end. In summary, we explored how to solve next greater element 2 using a monotonic stack, achieving an efficient O(n) solution. Remember the importance of data structures like stacks and concepts like circular arrays for problems of this nature. Thanks for watching, and stay tuned for more problem-solving tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!